Okay, so for tomorrow, make sure you check through the chapter 7 topics list. That we have kind of two big main topics as we're doing a lot of those logarithms and dealing with the log properties that were at the end of chapter 6, but we didn't test a ton on them. Solving exponentials using those logarithms and log properties, and then we dove into all the trig stuff. So sines, cosines, tangents, the graphs, the values, the unit circle, all that good stuff that we've been working through. There was some review material that we wanted to talk about as well that's on that topic list. And one of them is writing the quadratic in vertex form when it has an a value. So we did this early on. And what I'm going to do is just kind of go step by step through that. So for example, when we have an a value, we're going to have to factor that out from that front term. That allows us to leave a space here that I'll be able to complete the square with a thing on the inside, but remember that that adds a little nuance to this, that to find the number that goes in here so we can perfectly write that as a perfect square, I'm going to take half of b and then remember square it, and that's what goes in this spot. So half of b is -2, square it, and that is a +4. Okay, sorry about that, just getting the family line here, but half of b squared is a +4. And I can complete this square. This absorbs into an x minus 2 squared. But by writing that 4 there, I've actually added a lot to the equation. I combined it to this, but I needed to expand back to the original. So all we have to remember is that it's not just adding 4 to the equation, it actually added 16 to the equation. So I have to subtract 16 on the outside to keep it balanced and keep it the same. So I have that 4 up front, x minus 2, which would go to this, and then I have minus 13. Then moving on, we had a second part where we were finding the x-intercepts. I should have this as f of x equals. And you can always expand this to see if it does get you back up to that original, but determining the x-intercepts algebraically using two different methods. So, we have two forms here. This is standard form up top. We have vertex form underneath. Oops, I didn't want to move the whole problem. But what I could do to find the x-intercepts is set this equal to 0. That was a common, or what we do to find x-intercepts. And really algebraically solve from there. There's just one key thing that we always have to remember at the end when we take a square root. But the algebra for this is usually pretty straightforward and easy. Okay, and then I divide by 4, trying to get that square root alone. So I get 13/4. Write it as a decimal, but no big deal. All right, and then we take the square root of both sides, but as soon as I do that, got to make sure I have a plus or minus. So some of us are still forgetting that plus or minus, but after that, I just add 2. So I get 2 plus or minus the square root of 13/4. And that would be, if it is an x-intercept, I should write it as a coordinate. So as a coordinate, it'd be 2 plus or minus the square root of 13. Oop, I wrote that incorrectly. Well, what I could do, honestly, remember to take the square root of a fraction, you take the square root of the top and the square root of the bottom. So it might be a little bit cleaner to write it as square root of 13/2, just because I can take the square root of 4 pretty nicely. But then I added 2 to both sides, and this would be my final. The other way you could solve it is using the quadratic formula, which we've done a lot of. So going back to that 4x squared minus 16x plus 3, and I know what my a, b, and c are. So, opposite of b, 16 plus or minus, so on and so forth. I don't think we need to show that one per se for this test, but that's another way you could solve this. Next, we wanted to get into some of that chapter 6, chapter 7 stuff that we talked about log properties. So as a review, I was just going to write some of the log properties over to the side here. For example, log A times B equals the log of A plus the log of B, the log of A divided by B becomes a subtraction. And then our one that we use quite often, maybe I'll write it as log A to the B, and it has to be in those parentheses is B log A, where we can move that exponent in front. And on the chapter 6 test or 5-6 test, some of us were kind of getting away with using the log button or change of base on our calculator, and that's not going to work every single time. So we're going to be looking for these log properties, and some of them will have outcomes or like evaluate, or there'll be a final number answer, and some will just have some expression, and I'll add that onto this. So if I see a subtraction of logarithms, I know eventually there's going to be a division. And kind of the hint I usually give in class is if there's something in front of a logarithm, move it into the exponent first. So I would change this one to minus a log of x squared, okay? And then I can attack that subtraction, but I don't want to leave that in front. It's got to go to the exponent first because we're absorbing it into one logarithm. So to absorb it into one logarithm, we see the subtraction one over here in the bottom right says, well, just take whatever's next to the log in the front one, 7, over what's on the bottom, x squared. Okay, so that's the final expression for this. Now, later in the test or something, they might have this equal to something. So I might say equal to, we'll say, so let's say it's equal to 7. Well, I can solve this equation by using my log properties here. I changed it into one logarithm, and let's say hypothetically it's equal to 7. Oh, that one actually is going to be too big, sorry. Let's make it equal to 1. Not thinking through very well. So now it's kind of like the 5-6 test or this chapter 7. We're going to have problems like this, that if the base 10 here, it'd be 10 to the first, 10 to the first equals 7 over x squared. So see how I'm changing from my log form to my exponent form. Well, 10 to the first is just 10, and then I'm going to solve for x squared. I'm going to multiply both sides by x squared. I get 10x squared. Then eventually divide by 10, so I'll get x squared equals 7/10. Take the square root of that, plus or minus. Will work in this case because it is eventually going to take the square of it first. It's not in the base, okay? So we can set these log problems equal to something, or we might just have you absorb it into one log. So similarly, here I have a lot of coefficients, and I want to move those up into the exponents first. So I'm going to move a 1/2 there. I'm going to make a 2 up there to get it squared. So it's going to say the log of 49 to the 1/2, which we're going to talk about, plus log of 5 squared minus the log of 35. And if ever there's a time that you can actually find the log of it, like log of 10, make it 1. For example, here, the log of 49 to the half, 49 to the 1/2 is the square root. So it really becomes the log of 7 plus the log of 5 squared, which is 25, minus the log of 35. And let's see, we can combine, and when we have additions and subtractions, we just got to make sure we work left to right. So this would be the log. Now 7 times 25 is 175, divided by, because it's a subtraction, 35. And then just simplify your fraction as far as you can go. Maybe it becomes a nice answer in this one. I don't think, it'll still be the log of some fraction there. But yeah, I think that's going to be our final, well, not our final, you should simplify the fraction inside of that logarithm. But questions where we're expanding logarithms, we might have a logarithm that looks like this and one in an expanded form, or if it's expanded from there, absorb it into one logarithm. And a lot of times a common mistake is like putting the log of log 7 over log x squared and having too many logs. The whole goal is to bring it into one logarithm. So I wanted to go through similarly. I kind of went through a solving a log situation, but solving an exponential. That if I have, 6 equals 4 times 2 to the x plus 4, and just finding what x will equal to make this equal 6. So some things that we go through, and if we have, we could go up plus, well, let's go -2 or something on the outside here. We'll add on, is you got to do some cleanup work first. And this has actually been common on the test. Be careful when you're dividing like both sides by something. If you have multiple terms or you're separated by an addition or subtraction, many of us are just dividing by 4 and dividing by 4 and not doing it to this 2. So remember PEMDAS is kind of the order of operations of how we would compute something. SADMEPS, PEMDAS backwards, is how we have to undo it. So like SADMEPS, subtraction and addition is what we should move first. So if I have 8 equals 4 times 2 to the x plus 4, and then use your multiplication and division. So I'm multiplying by 1/4 or dividing by 4. So really this is 2 equals 2 to the x plus 4, which logically we could probably get to an answer pretty cleanly, but this is in exponential form. So remember, if we have 10 to the b equals a, that goes to log a equals b, with our base 2 in that case. So we'd have 10 to the, well, we can leave it in base 2, I guess. Let's do that. So 2 to the x plus 4, we can take, actually, let's practice with our log properties, even better. Let's take the log of both sides, just to show that again, and how we should solve our exponentials is using our log rules. That I took the log of both sides on purpose so I can move this exponent up front. So let's say the log of 2 equals x plus 4 times the log of 2. Now, this was just a nice kind of looked ahead. In this case, it's going to divide by log 2 on both sides, which is nice because this is 1. But if this wasn't, like if this was a log 3, you're just going to keep it as log 2 over log 3. And then my last step would be just to subtract 4. So in this case, x equals -3. Again, through the hypothetical, let's say this was in the original problem, instead of 2 to the x plus 4, it was 3 to the x plus 4. That doesn't affect this problem like that much. I would just go divide by log 3, divide by log 3. And really, this would not be as nice as the final answer, but you just write it out. Log 2 over log 3 equals x plus 4, and then subtract 4. So you get this, all of that minus 4 equals our x. So now that one will have a decimal. Sometimes you get really nice answers. Like I said, I kind of looked ahead to get that. It's going to follow the same suit. What we're looking for is get your exponent, get your base alone, and then take the log of both sides. That's the straightforward way of solving an exponential. Once you take the log of both sides, move that exponent in front, and then do any algebra from there. What I have for solving a log is this problem here. Like if it's in log form and I have an x involved, I might change its log form so it's one logarithm, but then change to base 10, or change to whatever base is given in your logarithm and change from log form to exponential form. Okay, so that's our logarithm stuff. Obviously the unit circle has been emphasized quite a bit, so I wanted to go through finding some exact values based on my unit circle, and talking through that. So with our unit circle, it kind of has everything, but we built it based on sine and cosine, where we learned that sine is the y direction of a coordinate and cosine is the x direction. So we really want to interpret what this is asking. Like in our calculator, it feels like magic that when I press cosine, it just gives me this decimal. But cosine is saying, what's the x direction of 3 pi over 4? And what you want to be able to do is draw that. Where is it actually being represented? We got to know the location of that angle. So I'll go to the the tool for that next time. But pi over 4s are 45 degrees. So here's a pi over 4. Remember, 2 pi over 4 is pi over 2. So then 3 pi over 4 is right here, kind of halfway between that vertical and negative x-axis. So it wants the cosine. So what we do is we always draw that right triangle. It goes from the central angle out, and then picture which one is the x direction. So my cosine, if I was to draw it or represent it with a picture, would be that red line. So that whole thing is this red line. Now what we notice is we could combine some of our geometry skills to see, well, if that is a nice 45, 45, 90 triangle, we know the ratios of those. All the ratios for over 45, 45, 90 are square root 2 over 2. Now, location matters, where you are in the circle. So this is in the negative x direction. So my final answer for this would be equal negative square root 2 over 2. So make sure you can draw it. Make sure you know your special right triangle ratios, and then work from there from the picture. So we'll try the sine of 2 pi over 3 here. I'm going to use my tools this time. Make it a little neater. Oh, that doesn't work. Get our circle tool. That looks a little bit better. Okay, so 2 pi over 3. You can practice with that unit circle. Know where those are, that I have a pi over 3, which is a third of that top half, and then 2 pi over 3, which we located right here. So there's that angle. I draw my right triangle, which I know this is 60. And that little angle there is 30. So however you know one of them across from the 30 is 1/2, across from the 60 is square root 3 over 2. And that would be my final answer because it's asking me for the sine of those. Now when you get to tangent, I'm going to use this same picture because it's at 2 pi over 3. Now remember, tangent is taking the opposite over adjacent, just like in SOHCAHTOA. It's just on our unit circle, every time our opposite is the y direction. And every time our adjacent is the x direction. So really, for tangents, it's not going to be as nice to see it on the picture, but we got to use the picture to help us. So for example, tangent 2 pi over 3, my y direction is square root 3 over 2. And then my x direction is right here, which is negative 1/2. So that's not my final answer. I got to simplify that a little bit, but that's what I'm going to calculate. I have the square root of 3 over 2, and just to help you see it, you've probably seen it more like this, where I have two fractions here, and I got to flip the second one just like we do in rationals. I got to flip the second, and then multiply, so it would be negative 2 over 1. But that actually works out fairly nice. For example, I get these 2's to, whoa, come back here. I get these 2's to cancel. So really the final answer is square root of 3 over 1, which is equal to square root of 3. That's our final answer for that. And then similar, maybe I'll move on from here, but if I have 5 pi over 6, that's right before pi, that's right here. So the tangent opposite would be 1/2 divided by negative square root of 3 over 2. And if you rationalize that, you get 1 over, or negative 1 over square root of 3, which would be a negative, which we can, again, rationalize that. If we don't remember, rationalizing was the beginning of this chapter, where we multiply by square root of 3 on top and bottom. So I get square root of 3 over 3. in the negative direction. So tangent is a combo of both x and y direction. So I believe the directions for this one was to convert from degrees to radians and radians to degrees. There's a nice little rule for that to help you if you get stuck, like you don't know if it's 0.5 radians, where does that actually land? You can put it in degrees, which maybe makes more sense from your background knowledge. But one way to simplify this is whenever you're going from degrees to radians, 1 degree is pi over 180. You're taking that top half and splitting it up into 180 equal pieces. So one degree is pi over 180, so I'm going to try and do 220 of them. So really all I have to do is simplify that fraction of 220 over 180, which eventually goes to 22 over 18. So that'd be 11 pi over 9. It's going to land on an exact 220. It's a little over pi. We can see which 220 is a little over 180. Similarly, if I'm going from radians to degrees, well, it's almost like the reverse action of this. So I would divide, anytime I'm going from radians to degrees, I divide by pi over 180. But that's the same as multiplying by 180 over pi. So this is not going to be a very nice decimal number here. So I'll use my calculator, not as a marker. Get rid of that. Let's see if I can now move this. Maybe not. All this stuff is in the way for my Zoom. There we go. So I'm going to take 0.5 times 180 and then divide by pi. So it's about 28.64, we'll say how many decimals, usually 2 or 3, 28-ish degrees, a little closer to 27 degrees. So I think that's enough examples, but same thing here. I multiply by pi over 180, and sometimes, sometimes they're nice solutions, and sometimes they're not, and it's all just based on that the visual. Like I could draw 0.5 radians because pi is 3.14, so 0.5 is only going to be 0.5. Here's 1, then 2, and then 3. So you can estimate it, and just remember radians can be in like decimals. They don't have to be in pies. It's just they're nicer seen in terms of pi. Another situation we dealt with was the Pythagorean identity, which is kind of a nice relationship that the sine of theta, or sine squared of theta, plus the cosine squared of theta equals 1. Because really what this is saying is x squared plus y squared equals 1. And in a unit circle, you're just doing the Pythagorean theorem. But we can talk about the sine squared and the cosine squared equaling 1 as well. So there's a couple ways to think about this. Is you can actually just plug in cosine here, that you square the top and bottom and subtract, and I'll do that. I want you to think of it or view it as another way. These show up on the ACT quite a bit. And think about what these two numbers are telling you. This is telling you that the adjacent is 5, or the x direction, and really it's adjacent over a hypotenuse, but in a unit circle, the hypotenuse is the radius. So I'm looking for an angle, or the sine of that angle, when I know the x direction is 5, and then the hypotenuse is 9. So when I look at it like that, like it's part of this bigger circle that's going around with a radius of 9, so on and so forth, I can actually find this x or this y direction here, because 5 squared plus that y squared equals 9 squared. So if I just do the Pythagorean theorem real quick, I get 25 plus y squared equals 81. Subtract that, it's not going to be very nice. It's not a Pythagorean triple per se. But what do we get? 56. And then take the square root of that, square root of that. This would be the square root of 56. And then really I just go with the sine. Well, the sine of x then is the sine of whatever this theta is, which is square root 56 over 9. And that would be my final solution. Similarly, I can use my Pythagorean identity here, where I know cosine squared is going to be 25 81st plus sine squared theta equals 1. And you got to deal with the fractions, which isn't, the worst, I guess. Sine squared theta then equals 1 minus 25 over 81. Now, what's nice with the Pythagorean identity, though, this is always going to be 1, so that would be 81 81st minus that would be my 56 over 81. Now, this is sine squared theta, where we put the squared in between, but it's just like thinking, hey, whatever the sine of theta is squared. So I can actually still take the square root. So let's say sine theta equals the square root of 56. Take the square root of the bottom, which is 9. And we got the same thing, or we would get the same thing. And if you have the right picture and have the right sine and cosine, can you find the tangent? Well, yeah, because I have that right triangle. Tangent is opposite over adjacent, which would be the square root of 56 over 5 for the tangent piece there. Okay, so sometimes they throw in negatives, and you just got to be careful. Like your hypotenuse is never going to be negative because it is a absolute distance here. But the x and y values could be negative, and you just place it in the correct position and then deal with that angle. And you can use just true Pythagorean theorem. You can plug it into this equation. Both work. And kind of find one that works for you. Back to full screen here. And lastly, we started talking about graphing sine and cosine. A little bit of tangent, but mostly sine and cosine. And then if we give you a graph, can you find all those pieces? We use the acronym MAPS, where MAPS was the midline, A was the amplitude, P is the period, and S is the shift. So in our case, it says state the midline, period, and amplitude for each. So remember, we have this like A sine B x minus C plus D, or sometimes we might use H and K. Either way, no matter what you call it, just know what that piece does. But the A, whatever in front of sine or cosine, is the amplitude. Now, technically, the amplitude is an absolute value. It's an absolute distance. So like if this was -2 sine, don't say -2 for the amplitude. It's +2. But that negative does tell us direction. So in this case, the midline, period, and amplitude, I want us to find the midline first, which is like I have a normal shaped curve, and it's going to be bumped up or down. In this case, the bump down is at -2. So I have the midline is halfway between the max and the min if I was trying to get it from the graph. So here's my midline is y equals -2. Should be a y equals equation as well when you're writing your final answer. We'll jump to amplitude. It's probably a little bit easier. Remember, amplitude is the distance, absolute distance up and down from that midline. So it looks like that is also 2. And then the period. Sometimes it's hard from the graph. Sometimes it's even hard from the equation. But remember, the b value is not the period. The b value helps me find the period, which is 2 pi over b. So in this case, the period equals 2 pi over 3. And if we look at our graph quickly, it's not the nicest scale for the x-axis, but it actually does work out nicely that this, if there were a tick mark, is 2 pi over 3. Because if I split it up into thirds, maybe that'll be a little bit helpful. 2 pi over 3, 2 pi over 3, here's 3 pi over 3. So it looks like one revolution for that is given pretty nicely. Not to mention, remember, or if we've seen, the period is how many cycles it takes to go in a 2 pi time. So if I keep going, I don't know exactly where it lands, or I didn't see that as 2 pi over 3. I could go, well, that's one cycle. Here's a second cycle when I get back to the midline. And here's a third cycle in that 2 pi time. So really, I did 3 revolutions in a 2 pi time. And that's another nice way to link that idea together. Okay, so Probably stop here with the examples. I'll close down maybe the recording, and if people have specific examples, you can always email me, but if you're in the chat too, or in the office hours, we're going to take care of those. But I'll post this later.